All right, let's get right into it. Today, we're doing a deep dive on a critical piece of power system design, the parallel operation of transformers. And look, this isn't just about textbook theory. We're going to focus on the real-world engineering principles, the stuff grounded in IEEE and IEC standards that every single system designer absolutely needs to have mastered. So, here's our game plan. First, we'll nail down the foundational principle. Then we'll map out the ideal conditions for success. After that, we'll get into what happens when things aren't perfect, and trust me, they rarely are, and look at the consequences of a mismatch. We'll then zoom out to see the system-level impacts and wrap it all up with the key design verifications that will save you from some very costly mistakes down the line. Okay, so to make sure we're all starting from the same place, let's get a really clear, standards-based definition. What are we actually talking about when we say parallel operation? The IEEE gives us our official definition right here in C57-153. Now, the phrase you really need to lock onto is common load bus. At its core, it's just two or more transformers working as a team, feeding power to a single point. This is obviously fundamental for building reliable, high-capacity systems, but it all hinges on that team being perfectly coordinated. So what does that perfect coordination actually look like in practice? Well, there's a pretty strict set of conditions that have to be met if you want to achieve that ideal state we're all aiming for in a design. The IEC 60176-8 standard basically gives us a non-negotiable checklist. You have to have the same vector group. That's to prevent massive, dangerous phase differences. You need identical turn ratios for equal voltage output. Matched impedance, that is absolutely crucial for making sure the load is shared properly. And of course, polarity, phase sequence, and frequency all have to be in lockstep. Getting even one of these wrong is going to introduce some serious headaches. And this quote right here, it perfectly captures the goal. In a perfect world with perfectly identical transformers, the load just divides up exactly as it should. Each unit carries its fair share of the work, and absolutely no energy is wasted in the form of these things called circulating currents. This is what peak efficiency looks like. Now, let's be realistic. The standards know that a perfect match is pretty rare out in the field. So IEEE gives us a hard number to work with for impedance, a tolerance of plus or minus 7.5%. As long as your transformer's impedances are within this window, they're generally considered good to go for paralleling. This number becomes an absolutely critical parameter for your design specs and for your field verification tests. But what happens when we step outside that ideal state? This is where the real engineering challenges start to pop up. Let's take a look at the consequences when these critical parameters just don't align. Let's look at this side by side. On the left, with matched ratios, everything's great. The system is healthy, the load is shared proportionally to each transformer's kVA rating, no problem. But on the right, you see even a tiny mismatch in the turns ratio creates a voltage difference. And that difference acts like a little pump, forcing current to discirculate between the transformers, doing nothing but generating heat and wasting energy, even when there's zero load on the system. And make no mistake about it, the scale of this problem can be absolutely massive. A small ratio difference, you might get a small, manageable circulating current. But a vector group mismatch, that is a whole different animal. You could be looking at currents that are approaching a full-on fault, which is, a catastrophic failure scenario we all want to avoid. So this table really boils it down for us. A difference in turns ratio is your main culprit for those wasteful circulating currents. A difference in kVA rating, though, that's actually what you want. It's how you get that proportional load sharing. But the vector group mismatch, that's the big one. That's the one you have to avoid at all costs because of the risk of destructive fault-level currents. Okay, now let's zoom out, because the consequences of paralleling transformers aren't just contained within the transformers themselves. They send ripple effects out across the entire electrical system. And the single biggest system-level impact is this. When you connect transformers in parallel, you are fundamentally lowering the total system impedance. And from a fault's point of view, lower impedance means a much, much higher potential fault current. And that, of course, has direct, practical, and sometimes expensive consequences for your design. Your circuit breakers, they might need to be upgraded to handle that higher interrupting duty. And it's not just them. Every single piece of equipment on that bus bar, the bus itself, the disconnect switches, the CTs, the VTs, it all has to be reevaluated to make sure it can actually withstand that new higher fault level. Here's another system-level factor to consider. How are the transformers being supplied? If they share a common source bus, you've created a very low impedance path, which makes those circulating currents from transformer mismatches a major concern. Now, if you have separate buses, that path impedance is higher, which can help. But, and this is a big but, now you've introduced a new problem. Any voltage difference between the sources themselves can create its own circulating current, totally independent of what the load is doing.
Okay, final section. Let's drill down on one critical component that often adds a layer of complexity to parallel operation, the on-load tap changer, or OLT. Getting the coordination right here is absolutely essential.
To make sure your OLTC-equipped transformers are working together and not against each other, you have to run these checks. First, are their control settings and deadbands properly aligned? Second, do they actually operate at the same speed? And third, and this might sound simple, but it happens, does a raise command on one controller actually correspond to a raise operation on the other? A simple wiring mistake here can cause the two units to constantly fight each other.
And if you get that coordination wrong, this is what you end up with. One transformer does all the heavy lifting, running its tap changer up and down constantly, while the other one just sits there, inactive. This leads to really uneven wear and tear on your equipment and, frankly, pretty poor voltage control for the whole system. You've basically paid for two regulating transformers, but you're only getting the benefit of one.
So let's just quickly review the most critical takeaways. Your success is all about matching three core things: vector group, turn ratio, and impedance. Don't forget that critical IEEE tolerance of plus or minus 7.5%. Any mismatch is going to risk generating wasteful and damaging circulating currents. Remember that paralleling will always increase your system fault levels, so you have to reevaluate your protection. And finally, if you've got regulating transformers, OLTC coordination is completely non-negotiable. And that brings us to the end. We've covered the steady-state principles from the standards, but that leaves us with one final question for you to take back and think about on your own projects. Beyond all the nameplate data and the calculations, what are the operational risks, the transient behaviors like inrush currents or sympathetic tripping, that are the easiest to overlook when you're designing and commissioning a parallel transformer system? Something to chew on. Thanks for tuning in.